Welcome to DocConf 2023. I have the honor to kick off the event with every architect's and developer's favorite topic, and that is how to build distributed systems and all the little surprises that come with that. And since coupling is sort of one of the very important aspects of that, I gave the talk the cheeky title of, well, I made everything loosely coupled, will my app fall apart? Or rather, it's about sharing my experience of building distributed asynchronous systems for 20 years and looking at what has changed, but also some of the problems that have stayed with us. My name is Gregor Hohpe. I just changed roles within AWS. I used to be an enterprise strategist and just joined our serverless engineering teams as a senior principal evangelist. And my history in building distributed systems goes far back when Bobby Woof and I co-authored the book Enterprise Integration Patterns back in 2003. So this is approaching its 20-year anniversary. Now, technology has moved on, so books also have. So more recently, I've written about the role of architects in architecture and about cloud computing. But today, it's really about distributed systems. And I'd like to begin by making a little plea for the line. We tend to think about systems as boxes, components, modules, classes, but also there are lines connecting them. And I'm convinced that we should be paying a little bit more attention to the lines, not just the boxes. And I'll show you why with a simple example. So here are two very simple systems that have four components, A, B, C, and D. Both systems are made up from the same components. The only difference is they wire together differently. The lines are different. Now, would you think that these systems have different properties? Well, it's kind of a trick question because obviously they do. You'll find that their properties are almost the opposite of each other. The system on the left has a very clean layered structure that gives it some nice abilities like replaceability. I can take C out and replace it with something else because dependencies are very clean. However, I might have more latency and I might also have a more brittle system because if C goes out, A can no longer talk to D. Well, the properties of the system on the right are almost the exact opposite. I have shorter paths and I have higher resilience in case C goes out. A can talk to D directly, but because I have more dependencies, it's going to be harder for me to replace one component with the other. So we see just by changing the lines, we give systems almost the exact opposite properties. And that leads me to my insight also about the role of architects. Don't just list the ingredients as your architecture. If you were going to say your architecture is A, B, C, and D, or whatever technology open source project it might be, you would have lost the difference between the system on the left and the system on the right. So think of yourself as chefs. Good ingredients are important, but the main role of the chef is putting things together, making a tasty meal. And the same thing is true for IT architecture. It's all about how it's put together. Your architecture is more than the list of ingredients. It is how you put it together to give it the desirable capabilities. And if that didn't quite convince you yet about the importance of the lines, let me dig a little bit deeper. We tend to draw these pictures. System A talks to system B. Now, well, how complicated can this be? Well, first off, what's the interaction model here? Is this synchronous? Is this asynchronous? Is this RPC? Is it a point-to-point connection? Is it a publish-subscribe connection where multiple people might be getting the same message? Many design decisions to be made. Well, also, is this depicting the data or the control flow? You might be using polling where control flow goes one way, but data flow goes the other way. So depending on that, the arrow is in the right direction or the wrong direction. Kind of important. Now, what about what goes on this wire? Like, what's the data format? Is A and B a system or an instance of a system? And then come all the distributed system fun aspects of partial failures, idempotency, duplicate messages, error handling. What's your conversation state? How do you undo things or recover from partial failure? So when we draw these simple lines, we're actually kind of brushing over some very, very important aspects. And that brings me again to building distributed systems is fun, and it gives us great capabilities like automatic scaling, but it also reminds us that we need to pay attention to the lines. Now, when we talk about lines, right, lines are the connections, the first word that often comes up is coupling. If I connect A and B, how much are they coupled? And the fact that this is not a new question by any means is easily found out by this favorite quote of mine. David Archer said, well, if you want to have things not be coupled at all, well, then just don't connect them. We have a very loosely coupled system that's not going to do much anything useful. And David Orchard is one of the early architects in BEA systems. So this is about a good 20 years ago. This is where ultimately web logic came from before Oracle acquired BA. So this topic has been with us for several decades. Now, I live in Asia, and I occasionally do some fixing on my apartment, and I also came to the conclusion that sometimes things are a little bit too loosely coupled, especially the wiring in my house. I sometimes wish this to be a bit more tightly coupled and a bit more organized, to be honest. So it's not about chasing one extreme or the other, right? If you find architecture saying everything must be loosely coupled, they're probably not a very good architects. Architects are in the business of trade-offs, understanding decisions and balancing considerations. So it's rarely that one extreme or the other extreme is always the right answer. We need to dig deeper. And if we dig deeper into coupling, we first need to understand what it really means. My favorite definition of coupling is that's a measure of the independent variability. If I change B, how likely is it that I also need to change A? Because that's what I'm after. I want to have the ability to change some parts of my system without propagating that change throughout all the other parts. That gives me some nice benefits. And change can come in functional change, but also operational change. What if B is slow or goes down for a small amount of time? Is A also going to be slow or down? Or is it going to be operationally decoupled? And I already hinted, right? It's rarely that one extreme or the other is the right answer. In all cases, architecture isn't that simple, and it's good for us architects that it isn't. So you need to consider that decoupling has a cost. You will have more moving parts. Asynchronous systems need queues and message brokers. They have odd states where queues fill up or you get tripped off by delays or asynchrony. So there is a cost of decoupling, and you have a benefit. So a classic decision to be made for architects. And it's not binary. Something isn't like tightly coupled or loosely coupled. It has many shades of gray. And here, just like a small sampling, these are all dimensions of coupling. Now, if I want to make a remote procedure call, am I dependent on the programming language? Like if I use JNI or something, I will. If I use HTTP and JSON or protobufs, I will not. Location, how do I find B? Is B an IP address? Is it a DNS lookup? Is it another level of indirection, right? And the list goes on. What is my data format? How do I encode integers? How about empty strings versus missing strings versus null field, UTF-8, right, versus ASCII characters, big endian, small endian? The list goes on, covering things like synchronous and asynchronous stack. Is there a call stack? Well, there isn't. So coupling has many dimensions, and all of those have gradations. So managing coupling is actually a very interesting topic for architects. And in fact, it's so interesting that my good friend Vlad Kononov is writing a whole book about it. Now, funnily, the book launch date has been pushed out a few times, telling us that this is actually a very complex topic. It's not because Vlad isn't working on this, right? It is just a very deep topic. So as give a tiny bit of a sort of preview of the thinking around coupling is you need to understand the strength of the coupling, like how tightly are the two pieces actually knit together? Like, is the tiniest change gonna trigger a change over there, or are they a bit more lenient? And then, of course, the distance matters, right? If these are two lines of code in the same method and I change the data type, that has a strength of coupling, but it has a short distance, so it's probably okay. I can use automated refactoring tools. Even within the same class, I'll be fine. But if I have something that goes far across the different system, then I have a bigger problem. And the last one, of course, is how likely is it that B will change? If B never changes, that coupling actually doesn't hurt me as much. Versus if this is something that I need to touch all the time and it can propagate throughout my system, then I have a much bigger problem. I like breaking buzzwords down into these dimensions. Now you can have an architecture discussion and decide where coupling or decoupling is really important, and maybe where some amount of coupling is actually okay, because it will save you design and runtime complexity. So my conclusion here is that the level of control you have over the endpoints actually determines how much coupling you can afford. If you're integrating with a commercial system, meaning you have very little control. I used to do this. I grew up with EAI, like enterprise application integration, right? Where you have major accounting system over here and order management system over there. You have very little control, and that means decoupling is the name of the game. But if I'm building a distributed systems and A and B are both my components, I can make a change on both sides. I can pass the same configuration parameters to them, so maybe some amount of coupling isn't as bad and will simplify my architecture and perhaps even give me better runtime performance. So context matters. I need to understand what kind of application I'm building. And I already alluded to an important distinction here. I said, oh, I'm building a distributed app versus in prior days, I used to integrate systems. Now, what's really the difference between the two? Well, they both look like this, right? I connected A to B, whether it's the accounting system or the order management system to the accounting system, or whether these are two lambda functions of my distributed component. In the high-level picture, they will look the same. So we need to consider context. And the context isn't just the technical stuff, it's also the organization, the timeline, and as you already saw, the level of control. So as it turns out, the answer to our question isn't apparent at all, or basically can't be answered if we look at technical abilities alone. It will look very similar. But if we look at the context, we will find out that there's quite a difference. I might be migrating data from A to B. I do this only one time with a separate team. And even though I have a low level of control, I do it once and I am done. If I have data synchronization, that is still likely done by a separate team, but I have a long delivery cycle. I'm separate from the application development. And if I'm building distributed applications, as I just alluded to, then I have a higher level of control. And we said that affords me some more coupling. And basically, connecting systems is the same as developing components, right? The difference between the lines and the boxes has gone away. So we see that once you look at the context, the level of the control, the timeline in which you do this, and who does it, then this difference becomes much more apparent. And that also explains, I work for Amazon Web Services, why we have different products for these different purposes. They all look like they're connecting one thing to the other, whether this is AppFlow or MQ, which is basically hosted versions of message brokers like RabbitMQ, right? Or whether it's the fully serverless components like step functions or EventBridge SQS SLS, right? They all look like lines, but you use them in different contexts, and that's why they are different tools. Context does matter, and in this case, it is what gives us the answer to our question of, are you integrating or are you building distributed applications? Well, it differs by lifecycle, team, and level of control, not the technicalities or the technical implementation. So with that preamble, let's dive into some of the hot topics that we hear today when we talk about distributed systems. Yeah, I work with serverless applications. Serverless applications tend to be fine-grained and event-driven. And there we have some interesting words, event and driven. As you already learned, as an architect, I like to dive a little bit deeper. So let's look at what an event actually is. So a lot of discussions about events versus messages. Now, Bobby and I worked on this many, many years ago, 2 decades ago. And in our view, the message defines the interaction style. A message means this is not a remote procedure call. There's no call stack here. You pass a piece of data from A to B. You might do that asynchronously, and that's it. There are no additional constructs in this interaction, like a call stack would do. Now, you can have different messages. You can have a command, do something, you can pass a document, or you can publish an event. So in my book, literally speaking, an event is a type of message. Message is the interaction style, and then the event is choosing a particular semantic of that element that goes across, of that piece of message. Now, this carries more meaning than it might initially appear. And many years ago, Martin Fowler has already reminded us that an easy trap to fall into is that you have an event, but the event kind of implies that something specific happens. It's like, hey, an order came in. Don't you want to like send the customer an invoice? And don't you want to ship the package? And don't you want to check the inventory? That's what Martin calls the passive-aggressive event, right? Or the passive-aggressive command. It's sort of disguised as an event, but it actually wants to be a command. So the semantics here are important. An event really tells you that something happened. It cannot presuppose what happens next, because that's decided by the consumer of the event. And that has a lot to do with, well, how do A and B actually talk to each other? How do I forge this connection, and what name do I give this? So let me stay with my simple example, right? Order comes in and somehow you need to take the payment for the order. So you could talk directly to the payment processor, right? We say, oh, this is more tightly coupled, but in some hand it makes things easy. You know who talks to who. If you want to decouple a little bit more, we don't name who we're talking to, but we say what we would like to happen. Classic command message, process the payment, right, related to this order. We can also take another step back and say purchase. It's more like a document message, right? An entity came in. Here's a purchase that perhaps took place, like a new purchase. So the order management system should know that that leads to a payment process. And if you want to, rather than a document, to make this a classic event, you would say order placed or order received. So you can see that you're shifting some of the responsibilities here. The top one, the left side needs to know what should happen next. At the bottom one, the right-hand side needs to know what it needs to react to. So the events don't automatically make the coupling go away. There's a little bit of a shifting here from left to right. If you're in an environment where the set of listeners changes a lot and there might be multiple listeners, you'll be happier with the bottom style. If this is a clear and stable one-to-one, then the top style might actually be okay. Again, it's about trade-offs. Now comes the next part. How do I actually connect A and B, right? How do I forge this? Like somehow I need to provide a reference, right? In a non-distributed system, we will do this with a pointer or a reference. In a distributed systems, it's a little bit more involved. So I can have what I call a composer. A composer creates this channel in the middle. It could be a message queue, for example, or a message channel, and it provides the name to both entities. We do this quite a bit. We use often DynamoDB as a connecting element, and we pass both Lambda functions the name of that DynamoDB, and that way the connection is forged. The nice thing is A and B have basically no knowledge of each other, because you have this magic composer that essentially draws the lines for you. Pretty nice setup. Sometimes you don't want that central element, though, because you want more dynamic. What if B wants to subscribe to this event on its own? You know, if that has to go through the composer, you sort of made a new point of maintenance. So if B wants to subscribe on its own, you can do this by the channel name and make that the connecting elements. So if A and B just know the same name somehow from the separate config files or wherever it comes from, then they are connected. Now, a name is a little bit simple, like it's either you match or you don't match. So most event-based systems have what's called an event or name hierarchy. Now, we do this with prefix matches in EventBridge, for example, where you can subscribe to a detailed set of events like all new orders only in the European Union, or all orders in the European Union, or all orders overall. Or if you want to be even more fancy, you can match on content, right? And with most messaging systems and serverless systems, like with SNS and with EventBridge, you can do that as well. You can define rules over the content. So the region might not be part of the channel naming, it might be actually part of the message. So again, you have a range of choices that will determine the level of coupling, the variability, and also the complexity of your system. There's no right or wrong answer. I often say architecture cannot be right or wrong. Architecture can only be fit or unfit for purpose. So first you need to understand your purpose, and then you need to understand the range of your options. And these kind of mental models and giving them names, almost like patterns, I come to that later, they help you make the right architecture decision. Now, when I started this section, I said event-driven. So there's two words in there. We talked about events and messages, right? Semantics of events and channels, and how that shifts some of the coupling, the connection making from left to right. But I also said driven. And the short answer I have is that your message-based system cannot make your application event-driven. Only your application can make itself driven by events, because the infrastructure, the transport, let's just transport events from A to B. Whether these events drive your application or not, that is decided by a different level. So quite a few years ago, Martin Fowler again gave a very nice summary of different options. Like event notification is the one we normally think about, where we say, hey, the address of this customer has changed. You know, the quoting system might want to know about this. Now, the catch is this event doesn't actually have the new address, so probably the quoting system goes back to the originating system and fetches that. It's a very lean way of publishing very small events, right? It's very frugal in a way, but you have sort of double coupling because every subscriber now needs to know where that's coming from. Of course, he can pass that address, the originator, along in the event, so you can play with this a little bit, but you have a more complex interaction. If you don't want that, you can do what we call event-carried state transfer. Now the event has all the relevant data. Now this looks simpler on paper, but operationally is often not as great as it looks, because you might end up with very heavyweight events, and the event source now needs to know what are all the data elements that all event consumers would like. Now that might be another form of coupling. If a new consumer comes around and needs different kind of data elements, you need to change the source. So you lost your independent variability, you lose coupling. So useful, but careful, right? Looks good on paper, not always as good in reality. And then there's event sourcing. That's a very different way of building applications. Here, different parts of the application talk to each other solely through events. This is almost like a database transaction log, where rather than making any update to your entities, you log the change in an event log. And that gives you some really cool properties, because you can replay history. You can go back in time and insert an event, replay that against your whole domain objects, and look at the difference. Accounting system or personnel systems do this. What if somebody entered the wrong time or the wrong number of hours for the last months? Now they say, oh, I actually worked that Saturday. I forgot to put that in. You need to go back in time, because this might trigger overtime and other benefits. But this is much more related to building applications. And then often, and Martin has it in his talk as well, so CQS, combined query segregation, is listed in this context. Again, something very much application-centric, not as much about building distributed systems, much more about how your front end talks to your back end, and basically having the notion that issuing a command against your back end uses a different domain model than actually fetching data from your domain model. So again, right, many choices here. Let's use these words more carefully. How you use the events involves the application architecture, and only then can you really describe what kind of event-based kind of application you have built. Now, events are a big deal. We like events. They make systems loosely coupled, scalable, extensible. But how does this all fit together with things like orchestration, right? Or do I need an event broker? So there are two kinds of routing events from A to B. The one is sort of the assumption of having an event cloud. Just, there isn't really a thing in the middle. The events just somehow, go from A to B. Maybe there's a publish subscribe channel here, like, SNS, like simple notification system that we have, right? But basically, the connection between sender and receiver is just made by publishing and subscribing. Quick side note, you guys might know that PubSub is actually one of my most unfavored terms, because a sub comes before pub, right? You subscribe first so you can get the published event. And secondly, publishing and subscribing are two very different actions. Publishing is a message-oriented action. You do it all the time. And subscribing is a meta operation. You do that only once. So it only sounds cute, but if you think of it as an architect, actually very poor name. So that is just the side comment. So rather than A and B and C figuring out what is the event that they need to connect on, right? We could say it can be the name or an event hierarchy, the channel name, or the event content. You could also have a broker in the middle, and the broker could decide what actually goes where. And conveniently, the broker could also translate the event. Because if B expects a different format than A sends, the broker can do some validation and transformation and the routing. So one is more like an event cloud, like in the middle is a pure transport on the right-hand side, and the middle is like a broker. We have something like EventBridge, right? Which one is the better one? Again, depends on your context. Do you want an element of central control, right? Or do you want this free-flowing, anybody can talk to anybody? In the past, it was like, we didn't like the broker so much because it could become a point of failure or bottleneck. In the cloud, that's actually no longer such a big concern. And the beautiful thing is, if you start out with a model on the left, you can actually inject an event broker without anybody really knowing. You just need the event broker to listen to the event that A publishes and do its thing, and A would never even know. Changing the topology here does not propagate. So we're loosely coupled with regards to our topology. And that is magical. And this is why we like events and loosely coupled systems. Now, I work a lot with orchestrations and workflows. Also at AWS, we have step functions as our serverless orchestrator. And the notion there is that a command on event comes in, and then what has to happen next. And then you have more passive components that respond to this central orchestrator. Works very nicely, right? If a request comes in, you need to fetch data from 3 different systems, aggregate the data together, send it back. This is actually perfect. In an eventing system, this picture turns a little bit on its head, because who talks to who is actually decided by the publishers and subscribers. You have this event cloud that we just saw. And what you do, rather, you sort of mine out higher level events from this event cloud, right? Classic examples, if you have an event for pricing change, and then you have a huge spike in order, that new event might be called pricing mistake. So this is a whole field. There's also an amazing area of process mining. Old friend of mine, Will van der Aals, work with that, and many startup companies coming around this now, basically allowing you to look at a flow of events and mining the process out. So rather than deciding the process up front, you observe and you mine the process. Very different game, exciting stuff that is going on here. A few final comments. Building distributed systems is complex. So, and whenever we have complexity, we like to abstract that complexity away to the extent that we can. But we need to be careful, because sometimes our abstractions turn into illusions. And one of those illusions is RPC, the remote procedure call. Some very clever people have the idea of, well, what if I make a distributed call, like a remote call across boundaries, system boundaries, maybe half around the world? What if I make that look like a local call? Because in the end, it's kind of sort of the same thing, except it isn't. The runtime aspects of a distributed call are very different. On top, you have shared state, low latency. It doesn't matter how many calls you make, and if something fails, it fails equally on both sides. You have a built-in call stack, so it's very convenient. On the bottom, it's very different. There's no call stack. You need to construct those. You have different systems. They hold different state. You have high latencies. You have perhaps packet or message duplication, and you have partial failures. So in this case, it's not a good idea to make it look the same. I call messaging an honest architecture style because it owns up to the limitations of the underlying medium. So RPC in most cases is a dangerous illusion. It's not a good abstraction for most distributed systems unless you have a really high level of control underneath. So we need to distinguish from an abstraction that basically makes the unimportant parts go away to an illusion which also omits some of the important parts and leads us down a sort of road of false comfort until we hit the wall, and nobody likes to do that. And George Spolsky said this, coined the law of leaky abstractions. He said basically all abstractions are leaky, especially when it comes to the physical aspects, like latency or partial failures. You just cannot abstract those away. So when you look to build abstractions, look carefully where these abstractions are coming from. We're often tempted to build abstractions from the bottom up, but I'm a much bigger fan to build abstractions from the outside in. What is my use case? What am I actually trying to achieve? And then use those as abstractions for building systems. And that's where the integration patterns came from almost 20 years ago now. We looked at what people actually build, and rather than sort of making technical patterns, we wanted to express what people do. Is this a message translator? Is it a message filter? Is it a message router? If so, is it a content-based router or a context-based router? We wanted to give people a new vocabulary and meaningful abstractions. And like very last is, I talked about 20 years of integration. You would expect that there's some cool stuff we can do now that we weren't able to do in the past. And that is the cloud is programmable. We have cloud automation. So when I build things like I did 20 years ago, making a loan broker, making a distributed system where you have a coordinator talking to different banks or processing loans, now I can make this programmable. I can map individual components, right? Here's a message filter I mentioned and an aggregator combining multiple messages. I can distinguish different languages to describe my solution. I can describe my solution in the business domain, quotes and banks and mortgages and a mortgage broker. I can also describe it in the patterns, right? Publish, subscribe channels, filters, aggregators, scatter gatherers. Those are the integration patterns. And then in a third level, I can describe as the running components, right? This can be SNS and Lambda and step functions and event bridge, right? Those are the AWS serverless components. Now, the interesting thing is that in the past, that vocabulary in the middle, like the patterns, that largely took place on paper. There was a pure design construct, and my implementation would only use the things on the right. So I ran the risk of losing these patterns, losing this design intent, because when I look at the build solution, right, it's much more just like the system elements. Well, this is where we can do some amazing things with cloud automation, especially with CDK, the Cloud Development Kit. It's like a first-class programming language. You can program your distributed applications using object-oriented language, TypeScript, Node, Python, Java. And now you can create abstractions. You can have a method that says, create me a bank. And now this actually deploys a physical runtime component based on the source code and based on the configuration here. You will have a running instance of a bank that can process requests. And you can do this in code. And now you can also program your patterns, like the message filter. Like, for example, you only want to filter valid messages that come back. You can do this and say, I want the message filter where this field exists. You see at the bottom here in the simple code example. or you can extract only parts of the message that comes. You do with a content filter and a payload filter. So this just as a small teaser, but to show you that in the cloud, the infrastructure becomes programmable. Modern cloud automation allows you to code abstractions. So now your patterns no longer live on paper. They're actually running code that deploys running AWS instances. And that is pretty cool. That's something you were not able to do 20 years ago. And you can start to think about now coding whole sequences of these kind of systems, right? Like expressing your whole pipes and filters architectures with a Fluent API and running this against an AWS cloud and actually ending up with a distributed system that has exactly the topology that you see here. Well, this is the stuff that I'm currently working on. And I think it's really awesome because you can code your architecture. You can now code your topology. This is no longer infrastructure as code. This is topology as code. So yes, some things have actually progressed a lot in the last 20 years. Right now we have automation. This is no longer give me a virtual machine. This is really express my topology. And when I run this code, I have a running instance of this distributed system. So with that, that was quite a bit of content for a keynote. A lot more good stuff coming throughout today and tomorrow. But as a quick recap, consider the lines. The lines determine the behaviors of your system, and think about the lines as their own construct. Coupling isn't binary. It's not on or off. It has many different dimensions, and there aren't easy answers like, oh, loose coupling is always good. Distributed systems versus integration is not a technical distinction. It's a distinction in context and timelines and teams and level of control that you have. And that also determines what amount of coupling is right for you. Events are all the rage now. Events are messages, and they invert the dependencies from the producer to the consumer. But whether you're event-driven or not, that is something you consider at the application level of your architecture. And yes, there's some complexity here, so let's try to abstract that away, but let's make sure that those are abstractions, not illusions. And if we want to do this in a really nice way, we can code abstractions, and those are things we can do with cloud automation and CDK. I always invite you to follow along my work. So I wear two different hats. The one is the architect hat, that's on architectelevator.com, and then I build actual serverless solutions, and that's on enterpriseintegrationpatterns.com. That is still the same website that has been around since 2003. And of course, I invite you to have a look at the books if you like thinking around the role of architects and how to build things in the cloud. There are some great resources for you. Thank you for listening, and I'll be online for the question and answer session. Thank you so much.